we have seen that if a function is analytic in some region, then the Cauchy-Riemann conditions are satisfied. The derivative is uniquely defined at every point, the derivative itself is an analytic function, and the function has an infinite all possible derivatives, and they are all analytic functions. Now what about integrating this function? Well, it turns out that if your function is analytic in some region R, say some function f of z is analytic here, then the integral of this function from a point z1 to a point z2 along some given line, for instance some given contour C, integral from z1 to z2 f of z dz, turns out to be independent of the actual path you choose between z1 and z2, as long as it is a connected path from z1 to z2 that never leaves the region of analyticity. So this thing here is independent of the actual path. From z1 to z2, it is independent of that. This should remind you immediately of a similar thing that happens in physical applications when you are looking at a conservative vector field, for instance, which can be written as a gradient of a scalar field. Then if you have a vector field u, which is the gradient of some phi of r, say, and you integrate this field from some point r1 to r2 like this, from point 1 to point 2 along some path, then grad phi dot dr, this thing here is equal to phi at r2 minus phi at r1. That is the whole point about using a potential when you want to describe a conservative force, for instance. Then you can deal with this potential because it is scalar as opposed to a vector, and the field itself is found by taking the gradient of the scalar, but the integration along any path is independent of the actual path, and it depends only on the endpoints of the path. An immediate consequence of this is that an integral del phi dot dr over a closed path of some kind is equal to 0. And the same thing is true here, because if this thing here is the same as that integral, then this integral plus that integral is equal to 0, and it immediately implies that the integral of an analytic function over a closed contour is identically 0, okay, a consequence of the Cauchy-Riemann conditions. This is called Cauchy's theorem. Integral, and I will denote a closed oriented contour by this symbol. I have to tell you the direction in which I go always whenever I write a closed contour, could be either direction, does not matter, f of z dz equal to 0 for any closed contour C. Okay. Equivalently, from any point on it to any other point on it, the integral is independent of the path itself. So you can actually deform this path like a rubber band. You can shift this all over the place as long as you do not cross the region of analyticity, you do not cross any singularities and so on. This thing remains 0, and it is so powerful a statement, it is a very powerful statement, and we are going to use that, exploit this all the time. This idea that you can deform or distort the contour of integration without changing the value of the integral. That is going to be a sort of central theme in a very large number of things that I am going to say, that this deformation of the contour does not change the value of the integral, and that is going to be exploited to the utmost. Okay. Now before we go on with this, and I want to show you how this can be exploited, we need to finally come to terms with the idea of a singularity of analytic functions, and let us do that. I will just remind you, since many of you have already come across simple examples of singularities. So let us start with them. The first and simplest class of singularity, which I am not even going to pay attention to, although one really should in a rigorous course, is the so called removable singularity, but we will get over it in a simple stratagem, as you will see. So there are these removable removable singularities, for instance, would be those singularities which look like the function is singular, but if you define the function appropriately is not singular at all. For instance, suppose you had sin z over z at this point. As z tends to 0, this thing becomes indeterminate, this quantity becomes indeterminate, but it has a finite limit, it has a limiting value, and the limiting value as z tends to 0 is equal to 1. So I could actually define this function as f of z equal to sin z over z for z not equal to 0 and equal to 1 for z equal to 0. Then I ensure continuity by doing that, and then this singularity at z equal to 0 does not exist at all, it is removed, it is gone. Okay. So by this trivial example we can make this a little more rigorous. I am going to get rid of removable singularities of this kind by assuming that the function is defined appropriately by a limiting value so that continuity is preserved and so on and so forth. Okay. So we will not pay any more attention to this kind of thing, look at really actual singularities. Okay. Now analytic functions themselves, recall that non-singular ones we wrote in the form n equal to 0 to infinity, some coefficients Cn z minus z naught to the power n. By the way, let us okay, we will leave this z naught as it is for the moment, but since I am going to use z naught for other purposes, let me use the symbol a here. Okay. In other words, I am describing a function near the point z equal to a, and the claim is if it is analytic at z equal to a, then I have a power series, a Taylor series convergent inside some circle of convergence about the point a. Okay. To this non-singular or regular part, I could add portions which have specific singularities, and the simplest of these is when the function looks like f of z equal to some coefficient c divided by z minus a. So in addition to non-negative powers of z minus a, there is a negative power to power 1, and to remind myself that this is z minus a inverse or minus 1, let us call this coefficient c minus 1 plus this portion. Okay. So if in the neighborhood of z equal to a, some point a function has this kind of behavior, namely most of it is a Taylor series which is analytic at z equal to a, but there is a portion which diverges, becomes infinite at z equal to a, and it has a behavior which goes like 1 over z minus a precisely. Then this function is said to have a simple pole at z equal to a, and the residue at this pole equal to the coefficient c minus 1, and you will see a little later why this residue is so crucial. Okay. In fact, the whole of complex integration is sometimes called the calculus of residues, because we are going to be evaluating residues of various functions. Okay. And this part is a singular part, and this part is a regular part. Now this singularity may not be overt, may not be always obvious, you may have to work a little bit in order to extract this residue. For instance, suppose you had this function sin z over z squared. What sort of singularity does it have near z equal to 0? It is clear this function is blowing up at z equal to 0 because there is an extra power of z in the denominator, but what kind of singularity does it have? Well, what you should do is to take the sin z, which we know is an entire function, and expand it in a power series in z, and then divide by this 1 over z squared and see what happens. This of course is equal to z minus z cubed over 3 factorial plus dot 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 divided by z squared. So it gives you a 1 over z minus z squared over 3 factorial plus regular part in this fashion. And it is precisely of this form. These are non-negative powers and they form the regular part, happen to converge for all finite z in this case, but this portion is singular at z equal to 0, and what is the residue? It is the coefficient of 1 over z minus a, that is the residue at the point, and what is the residue in this case? It is just 1 unity in this case. So in more general circumstances, if you had f of z equal to say g of z over h of z, ratio of two smooth functions, analytic functions say, and let us say at g of a is not equal to 0 and h of z has a simple 0 at that point. So this means that h of z is of the form h of a, which is 0, plus z minus a h prime of a plus higher orders, and g of z is analytic, so it is g of a plus other terms, and g of a is not 0, let us say. Then what can you say about f of z at z equal to a? What sort of singularity will it have? Well, in the neighborhood of z equal to a, this goes like g of a plus z minus a g prime of a plus dot dot dot, and this guy here in the denominator goes like z minus a h prime of a plus higher order terms. Okay. So it is clear that in the limit as z goes to a, this term dominates, this comes out, and it has a coefficient which is g of a over h prime of a. Okay. So what sort of singularity does it have? Simple pole, but what is the residue? G of a over h prime of a, and that is a very useful thing to remember. So one could ask, what is a general formula for this function? Suppose I say f of z has a pole, a simple pole at z equal to a. Residue, what is the residue at this point? How would you do this? Well, remember it is of the form c minus 1 over z minus a plus a regular part. Now to extract that c minus 1, the obvious thing to do is to multiply by c minus by z minus a, and then let z go to a. So it is immediately obvious the residue is equal to the limit as z tends to a, z minus a times f of z. Because this fellow will have c minus 1 over z minus a, which will cancel this, and the next term will be a regular part, but if you put z equal to a after multiplying by z minus a, it vanishes. So that is the quick way of extracting the residue. All you have to do is to do this. Where does this function 1 over sine pi z, where does it have singularities? Sine pi z itself is an entire function, we know this, and it vanishes, sine pi z vanishes whenever z is equal to any integer, 0, 1, plus minus 1, plus minus 2 and so on. So where does this function have singularities? This is cosecant pi z. Where does it have singularities? At all integers. At every integer it is singular, it blows up. What sort of singularity is it? Well, the only one we have studied so far is a simple pole, right. So the singularity is a simple pole at every one of these points, because sine pi z has a simple 0 at that point. Simple 0 at z equal to a means it is of the form z minus a and not z minus a squared or cubed or anything, which are higher order zeros. So this function has simple poles at all the integer values. And what is the residue? Well, it certainly has a singularity at z equal to 0, right? That is immediately obvious. What does sin pi z do as z tends to 0? Tends to 0, but always you have to tell me not the limiting value, but what is the leading behavior. What is the leading behavior of sin pi z as z goes to 0? Pi z itself. And now I have 1 over sin pi z, so what is the leading behavior? 1 over pi z, right? And what is the residue? 1 over pi at that point. Now what is the residue at the other points? What is the residue of this at z equal to n? You have to do this. So you have to find the limit z tends to n. You can use the periodicity, sure. Yeah. But it is interesting to do it, blindly apply the formula. So z minus n over sin pi z. Find the limit of this. Okay. The reason I am doing this is because they studied this L'Hopital's rule for finding the limits of ratios which become indeterminate in high school, and after they got through the entrance exam they burnt the notes and danced on the ashes. So now I would like them to go back to that. Tell me what this is. What is this equal to? Quick. Differentiate this and set z equal to n, and then what happens? You differentiate this, you get 1, you differentiate this, you get pi cos pi z. And what's cos pi n? Minus 1 to the power n. So this thing is equal to minus 1 to the power n over pi. Okay. So you are guaranteed that cosecant pi z in the neighborhood of any z equal to n, any integer n, goes like minus 1 to the n over pi plus a part that is regular at z equal to n. The part that is regular at z equal to 2, for instance, will lead to a singularity at z equal to 3. It will contribute to the singularity elsewhere. So you have to be careful. At each point the residue might be quite different, as it is in this case. Okay. So we will use the idea of residues, finding residues of functions quite extensively, but you should be very quick at finding these limits, these points. But this is a very simple algorithm for finding the residue at a point. But now you could ask, we talked about simple poles, what happens if this function f of z has what are called multiple poles, multiple or higher order poles, multiple poles. So f of z is of the form, there is a regular part n equal to 0 to infinity c n z minus a to the power n, which may or may not terminate at some point, we do not care, but it is convergent certainly in some region, some circle about z equal to a, plus a portion which is c minus 1 over z minus a, plus let us say there are however higher order terms here, more negative powers, and it starts at some c minus m over z minus a to the power m plus dot dot dot, etc., where m is an integer bigger than 1. Then this function is said to have a pole of order n. At z equal to a. Okay. So if it turns out that in the neighborhood of such a point a, this function has a lot of negative powers of z minus a, terminating at the highest power, some mth power, z minus a to the power minus m, and then less singular terms and then a regular part here, then this function has an mth order pole at z equal to a. And for reasons which will become clear, we are interested always in the residue. But remember, the residue was defined as the coefficient of z minus a to the power minus 1. This term is the important part, this thing here, and we need to find this term. Now the question is, how are we going to extract this term? Earlier we extracted it quite simply because this thing had c minus 1 over z minus a plus a regular part, and all I did was to multiply by z minus a and then said take the limit z goes to a, I got c minus 1. You can't do that now because these things will blow up. So how do I zero in on this coefficient c minus 1? This is the residue. It is still the residue at the pole. How do I find that? What would you suggest? What limiting procedure would you suggest to do this? It is clear I must multiply by z minus a to some power, and then I must set z equal to a, but any power less than m is going to land me in trouble here. So I multiply by z minus a to the power m, f of z and a, and this series, this regular part converges inside here. Let us call this radius r1. The regular part converges inside this circle of convergence of radius r1 say. Since this is an infinite series with negative powers, you should also ask what is the radius of convergence of this thing, otherwise it does not make sense, it should converge, right. Now this radius of convergence will specify a region outside which this series converges, because if you put 1 over z minus a equal to w, for instance, some other complex variable, then it is a power series in w, and this in positive non-negative powers of w, and that will converge for mod w less than some number r2, or if you like mod z minus a greater than this 1 over r2. So it is clear that this series actually converges outside some neighborhood of z equal to a. So perhaps it converges in a neighborhood like that, outside. So we are stuck now. You cannot write a representation like this because this portion requires you to be inside here, but this portion to make sense requires you to be outside there. The only way that you can make sense out of such a representation is if this regular series converges inside some r1 and the other series converges outside some r2, and everywhere else it converges outside. Then in this overlap region between the two, which is an annular region, both series converge, and this series representation for this function makes sense. So typically series of this kind, they call, by the way, they call Laurent series, and they would typically converge in some annular region always. So you require that r2 less than mod z minus a less than r1, typically in a region of this kind. Okay. It could be that r2 shrinks to a point, 0 alone, and it could be that r1 extends all the way to infinity, that is possible. Here is an example. Consider this function. Consider the function e to the power 1 over z. Okay. This function is of the form 1 plus 1 over z times 1 factorial plus 1 over 2 factorial z squared plus etc. Okay. So it can be written in the form summation n equal to 1 to infinity 1 over n factorial z to the power n, that is the singular part here, plus 1 in this case, that is the regular part at z equal to 0. So all negative powers, negative integer powers of z appear in this series, and the series converges as long as, well, e to the power z converges as long as mod z is finite. So e to the 1 over z converges as long as 1 over mod z is finite, which means mod z is not 0, that is it. So this series converges in mod z greater than 0 outside the origin. Where does this series converge? It is a constant, it converges everywhere, including the point at infinity. So this whole thing converges for mod z greater than 0. So this representation of this function is valid in the region of the punctured disk. There is an essential singularity at the origin, an isolated essential singularity at z equal to 0, and this Laurent series converges everywhere outside the origin, including the point at infinity. So in this punctured disk, in this punctured plane, it converges everywhere. What is the residue of this function at z equal to 0? It is the coefficient of 1 over z always. What is the residue? It is just 1. Okay. Suppose I added to this, suppose I added e to the power 1 over z plus e to the z. Now what does the Laurent series look like? Well, as before, I could write this as summation n equal to 1 to infinity 1 over n factorial z to the power n plus the n equal to 0 term here. The n equal to 0 term is 1 here plus 1 plus summation n equal to 0 to infinity. If you like, I will write it as 1 to infinity z to the power n over n factorial, and then write a 2 here. It's 2. Okay. Now what does this converge for? Where does this converge? Mod z greater than 0. So this requires that mod z be greater than 0. So in the complex plane it says everywhere except the origin it converges. And where does this converge? All finite mod z, so mod less than infinity, mod z less than infinity. So where does the whole thing converge? In an annular region, although you do not see the annulus, in the annular region 0 less than mod z less than infinity. So on the Riemann surface, on the Riemann sphere, it converges everywhere except at the south pole and the north pole. Except at those 2 points, the south pole, remember, is the origin on the complex plane, and the north pole is the point of projection, is the point at infinity. So on that sphere it becomes easier to visualize, it converges except for the 2 poles, except those 2 points, it converges everywhere, this function here. Now what about this function? What about e to the 1 over z squared? What sort of singularity does it have and where? At the origin, yeah, it is at the origin. And what sort of singularity is it? Is it a pole of finite order or is it an essential singularity? It is an essential singularity. What is the residue at the origin? 0, it is 0. The residue at the origin is 0 in this case, because there is no 1 over z, there is no 1 over z anywhere. What about this? What sort of singularity does it have? Essential singularity at z equal to 2, and the residue is 0. There is no coefficient of 1 over z minus 2, so the residue is 0. What about this? It's got an essential singularity at z equal to 2, alright, because those negative powers can't be finished by this single power of z minus 2. And what is the residue? Minus 1, because you have got to take the leading term here, 1 minus 1 over z minus 2 whole squared, and that gives you minus 1 over z minus 2. Okay. What sort of singularity does that have? Essential residue 0. There is no 1 over z minus 2 term possible in this case, and so on. So you can compute residues in various cases, and let us come to why this residue is so important. Why are we making such a big deal about this residue? And the reason is the following. And the reason is buried in a property of integrals, which is very, very simple to state but extremely powerful, and let me state this thing here. So consider this integral z to the power n dz over a circle which over a closed contour which encircles the origin. By the way, this function z to the power n is an entire function. It is for positive integer value of n, a non-negative integer value of n. It is an analytic function everywhere except at z equal to infinity. So it is clear that if you encircle the origin once in this fashion in a closed contour C, this is equal to 0 for n equal to 0, 1, 2, etc. It is clearly equal to 0 immediately. Now we can prove this in many, many ways. One of them is to say, well, as long as you are in the region of analyticity, you can distort this contour, so you can actually shrink it to a point and then it disappears altogether. Or you can, if you like, say that it is the same as an integral over the unit circle. This thing here is equal to an integral over the unit circle, and on the unit circle, on this circle, z equal to e to the I theta, because r is 1 on this circle, and then dz equal to e to the I theta I d theta, and this integral dz z to the power n is equal to integral from 0 to 2 pi e to the n plus 1 I theta I d theta, and this is equal to 0 because you get cosines and sines from 0 to 2 pi and everything vanishes. Okay. So for all non-negative integer values of n, this integral is 0. Okay. What happens if you had negative powers of, so consider dz divided by z to the n plus 1, where n is 0, 1, 2, 3, etc. Okay. What happens to this integral? I play the same trick, but here now this has a pole at z equal to 0. What is the order of the pole? N plus 1th order, is a pole of order n plus 1, whatever be this n, and now I write that integral down, which is perfectly alright because the singularity is at this point and the contour is not passing through the singularity, so it is perfectly well defined in that region. And then what happens? You get this equal to integral 0 to 2 pi d theta, and then there is an e to the I theta I d theta, that is dz, divided by e to the n plus 1 I theta, which is equal to integral 0 to 2 pi d theta e to the minus n I theta, and then an I. Okay. What is the value of that integral? Well, when you put n equal to 1, 2, 3, etc., it is certainly 0. What happens if you put n equal to 0? Then it is 2 pi, then it is 2 pi clearly. So this integral is also 0 except when n equal to 0 out here, and then the answer is 2 pi I. So it follows that this integral (1 over 2 pi I) integral over a closed contour encircling the origin once in the positive sense, that is why you run from 0 to 2 pi and not the other way about, dz over z to the power n plus 1. Whenever n is 0, the answer is 1, and when n is any other integer, positive or negative, the answer is 0. So this is equal to Kronecker delta of n with 0. It is a crucial result. Okay. So it vanishes except the coefficient when it is 1 over z in this form. And of course you can immediately generalize this and say, instead of this contour, we look at a point A and you look at a closed contour which encircles the singularity at A alone, and you could replace this by z minus A to the power n plus 1, and this contour C encloses that point. Okay. And then except for the term which goes like, except if this integrand goes like 1 over z minus A, the answer is 0. So now it immediately follows that if you have a function with poles and z equal to A is some pole, and you integrate f of z dz around a contour, simple contour which encloses this pole once in the counterclockwise sense, what will this be equal to? Because it has got a pole or maybe an essential singularity at that point, you expand this in a Laurent series about the point z equal to A. And then as long as you remain in this contour remains in a region where the regular part is still regular, it is immediately clear that all the terms are going to be 0 in the singular part, and definitely in the positive regular part they are already 0 because of Cauchy's integral theorem. The only term that will contribute on the negative side is the one that is the coefficient of 1 over z minus A. And what is the coefficient of 1 over z minus A? The residue. So this is equal to 1 over 2 pi I times this equal to the residue at z equal to A of f of z. So this is Cauchy's integral formula, and that is going to help us evaluate a large number of integrals. Okay. So what it does is to reduce the evaluation of a line integral, a contour integral, to an algebraic operation of just finding the residue of the integrand at that point. Okay. And we will see how powerful this statement is. And all you have to do is to evaluate this out here. Suppose this contour went around twice, what would happen? The whole answer would be twice. If it went around twice in the negative sense, what would happen? Minus 2 times this. So if it has a winding number of r around this point, where r is either positive or negative depending on the sense in which the contour is traversed, then the answer is minus 2 pi I r times the residue at that point. What is this equal to? E to the power 1 over z integral around the origin dz. So this, there is an essential singularity here and this contour looks like this. What is this equal to? This has got a bad singularity at z equal to 0, it is an essential singularity, but we do not care. All that you are interested in is the residue at that point. What is the residue at that point? 1. So what is this answer equal to? 2 pi I. You are guaranteed that. What is this equal to? 0. You are guaranteed that. There is no residue at that point. It is equal to 0 at that point. Okay. We will look at a large number of many more complicated examples, but this is a very, very simple way of doing things. All you have to do is to find the residue at that point. And there are going to be a large number of tricks for changing this contour to other contours and so on, all exploiting the fact that it is deformable in this fashion.